But let's look at one of these answers. The square root of negative 125. Someone is saying that it is equal to negative 11.2. Can someone push back on that for me, please? All right, so one of the answers was negative 11.2. Can you grab the markers on the first side? Pause where we are, look at the thinking, let's talk about it. Why should we know that the square root of negative 125 cannot be negative 11.2?
Because they're going to be a negative.
So, a square root can't be a negative. Now, if we take the square root of a negative, we should get what number? We should get an I in there. We got to pay attention to that. What I would remind you of is this. If the square root of negative 125 was negative 11.2, that means negative 11.2 what would equal negative 125? Think about it. If the square root of negative 125 is equal to a negative 11.2, what could you do to negative 11.2 to get to negative 125? Yeah. Is that possible? What's a negative times a negative? A positive. Remember, that's the whole reason that we need an I here. Now, I will say this. If you take the square root of 125 in your calculator, it will be about 11.2, but it's an irrational number. It doesn't stop there. Remember, we talked about simplifying this, and I saw a lot of us getting to work there and starting on this. When I want to simplify a square root, what kind of factors do I need underneath that square root? Come on. I need people to engage. You can't learn if you're not engaging. What kind of factors do I need under that square root to simplify? Right? You can't take the square root unless it's a perfect square. So, Miracle, do you know of any perfect square factors?
No.
None at all?
No.
No hint? Just looking at negative 125?
25.
Possibility of a 25, right?
50.
Maybe a 50?
100.
Maybe 100?
70.
Now, let's pause for a second and remember. Factors are something that you would be able to multiply by another integer and get 125. Or, think about it, can I take 125 and divide it by 100 and get a whole number? It's not 100. Can you take 125 and divide it by 50 and get an integer? But could I take 125 and divide it by 25? 1, yes. 2, which of these three denominators are perfect squares? Not 125, just the 25, right? Remember, we need perfect square factors. We need things that are perfect squares that we can divide out. And so, when I look at this, how would I factor negative 125 to simplify this radical? What's the first factor that I definitely need because it's a negative 125? Don't forget to start with the square root of a negative 1. Because what is the square root of negative 1? This is the whole point that we're dealing with. It's I, right? We're going to eventually get to an I. We're not going to start there right now, but the square root of negative 1 times what's the perfect square factor that we identified? 25. And what's the factor that's left? 5. 25 times 5 is that 125 times negative 1 is negative 125. Now what do I do? Remember, I have 3 factors. So I separate into how many square roots? 3. What's the first square root? Times. Oh, still the square root. So make sure we're clear of that, right? Times the square root of 25 times square root of 5. Jose, tell me one of those square roots that I can easily simplify. The square root of 25 is what? Is 5? Anybody want to push back on that, or are we good with? So notice when I take that square root, am I still going to have? Am I then going to say square root of 5? No. Remember, the square root of 25 is 5. So in its place, I just leave a 5. Are there any other of those square roots that I can easily simplify or rewrite? I'm rewriting -1. What is I though? So we need that whole square root, right? Remember the square root of -1 is I. And can I easily simplify the square root of 5? So I leave it as is. Now, traditionally, what goes at the very end? So I'm going to go 5 square root of 5 I. What are your questions before we continue? I noticed some of us were making certain things more complicated, but don't forget you want those factors. You want the factor of -1 because the square root of -1 is going to give me my I. I want a perfect square factor. And guys, you don't have to know those off the top of your head. What do you have at the tips of your fingers that can help you out a whole lot? Calculators, right? Like, take advantage of that. I feel like so often I see students who are like, oh, I just struggle with math and that's it. No, for the calculations that we struggle with, use a calculator. Like, you can pick up a calculator and do 125 divided by 2 or 125 divided by 4. Now, neither of those are factors, so it doesn't actually divide it except giving you a decimal or just leaving it as a fraction like Jamarcus found. You need perfect square factors. Okay, quick note here on the square root of -30. So some of us started to rewrite this, right? Square root of -1 times 15 times 2. That's a good way to think about it. Oh, this is the thing I was forgetting. Please do note, is that I underneath the square root? No. I is the square root of -1, so do not put the I inside of the square root. You've already rewritten that square root of -1 as I. But over here, like someone rewrote it like this. Will the factors of 15 and 2 help me simplify this radical? Yes? So do you know what the square root of 15 is, Jamarcus? What was 5 was the square root of what? 25, right? Think about it. We need our perfect squares, right? When I look at perfect squares, 2 squared is 4, 3 squared is 9, 4 squared is 16, 5 squared is 25, 6 squared is 36. That's even more than 30. Are any of those factors of 30? No, I'm just kidding. Great job, guys, right? Like, none of those are factors of 30. So can I actually simplify that part of the radical? I don't have to do anything other than just write it as -1 times 30. That's the square root of -1 times the square root of 30. And what's the square root of -1? I. So I'm actually just left with the square root of 30, I. If there are no perfect square factors, you don't simplify the radical, you just leave that radical and then you have the I afterwards.
I thought you said you could do
Ask your question.
I'm not saying
Okay? Do your best. Talk through.
like adding 2 to equal 30. Not to like adding 2 numbers to make 30. Like,
Okay. It needs to be factors. It has to be things that can multiply. Okay? And we want factors that are perfect squares, because remember, what does a square root undo? What does a square root undo, Eliza? So, I need a factor, something that's being multiplied, that is a perfect square. If it's not a factor, can't do it, and if it's not a perfect square, you can't do it. Okay? That property, guys, where I split it into multiple radicals, only works with factors. That's it. Does that make sense? So you cannot do that unless it's perfect squares and factors. Questions, comments, concerns before we start reviewing for the test? Or continue reviewing for the test? I told y'all there will be a couple like this on the test for sure. And when you solve quadratics, you will have to simplify radicals to show me complete mastery of those skills. Going once. Going twice. Means we're all going to master this part, right? Knocking it out of the park. Whew, we are dead today. Y'all, it's only been half a week. Now granted, I guess some of y'all had the ACT, but... P.S. What's been going on here at Hillcrest? Like, what happened with all the fights yesterday? Weren't there like multiple? No one knows? Cool, that means that we ain't involved in them, that's good to know, or hearing much about them. Yeah, there are people being crazy. But y'all staying out of it, I'm proud of you. Alright, so, why are we here?
Mr. King, I see how you're racing.
By the way, guys, when you write on the desk, don't forget don't be aware that tissues actually erase the desk really well too. So you can just grab a tissue. So, why are we here? To learn how to make arguments, which means we need to learn how to communicate and to think and to learn and to grow and reach our capabilities, as Ms. Dubberly reminded some of us yesterday. Right? So guys, your brain is a muscle, or your brain is just like your muscles. You can only reach your potential, reach your capabilities by being challenged, by growing. Take advantage of the resources you have. I was talking with a student from second block when he was being an office assistant yesterday, and he was like, Mr. Keenan, we should just done our test tomorrow because I'm not going to study over the weekend. Make a choice to study. You cannot reach your potential if you don't take time to study. Literally, I looked at him and I said, well, what do you plan on doing next year? He's a senior. And he goes, I'm going to go to Shelton. I was like, well, then you better get used to studying over the weekend real quick. Ms. Bauer's smiling in the back because she's 100% in agreement. You can't survive college, guys, without doing some studying. You may have done that in high school in some places, but I promise you, the only students that I knew who were successful in college were the ones who learned how to study. If you don't, yikes. And like, I get it. I made it all the way through elementary school, all the way through middle school without having to study a lick. But then I went to a really tough high school, and I had to study a lot. But I tell you what, I was well prepared for college. Knocked it out of the park. You gotta study. And it's not bad, it's good. No, is it as entertaining as TikTok? Heck no. Is it as entertaining? Because I know that doesn't connect to some of us. I feel like Marshall's probably never looked at TikTok in his life. No? You like TikTok? I don't know. It may not be as entertaining for some of us as others. Some of us may prefer to go out mudding or whatever else, but studying is good. Okay? So, we're going to finish, we're going to review for the test. We are going to start the next unit in the last 45 minutes of class today. So, remember this last unit, or last lesson here, nothing is new about solving quadratic equations. What are the 3 ways that you can solve a quadratic equation? So you can convert it to vertex form. So we got to know our vertex form. We have to know how to identify it, A, H, and K. But when you get vertex form, what do you have to do? Use inverses with properties of equality. What's another method to solve a quadratic? No, not ask Mr. Kinney. But use the zero product property. What do we have to do, though, in order to use that zero product property? Well, it has to be set equal to 0, and we have to use the AC method of factoring, or just factor in general. And then what's the last method? Use that quadratic formula. Guys, I do want to point this out. Like, I go through these 3 things pretty much every single day. These are 3 great things to write down on a flashcard and to go through them and remind yourself of how to do them, or what, put on a flashcard, 3 methods to solve a quadratic equation. And you go through bang, 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 right? And say it out loud, talk it through. Read it over and over again. We've talked about these things. You've got to know these ideas because you have to know when to identify each. And you have to be skilled in it. You need to take time to practice these skills over the weekend. You have plenty of problems in the book. You can go back onto Matthew and review. I've already told you exactly what the test is going to look like. Take advantage of that. Over half the test is going to be, it's only one side of the page, but it's definitely the majority of the test. It's 8 questions. 8 quadratic equations. You have to solve 6 of them. You choose which 6, but you have to use each method at least once, and then the other 3, you get to choose however you want to do it. But that's going to take some time, especially if we're not used to solving. Alright, so here's the review that we're going to use. Here's 3 practice problems. I don't believe we got to any of these 3 last week or yesterday. So we're going to get to the vertical surfaces. We're going to practice solving these. Leave your work up there, but then move to the different questions when you get there. This is on page, I don't know because I didn't write it down. I know. Let me go look. It's somewhere around 108 or something like that in the book. It is officially 109. Page 109 is where we will find these three equations. We're going to solve these three. I'll leave them up on the board, but you can bring your textbook. But let's get up to our vertical surfaces. Let's actively collaborate to do our best to master solving quadratic equations. This is our last time in class. Ms. Bauer's here to help answer questions. I'm here to help answer questions. Let's get up, let's move, let's learn. Come on. Woo! If you focus on the big picture, it's not too many steps because you have small chunks instead of big chunks. You don't have to just memorize it all. What I need you to remember is this. Let's write down a summary of the big picture. When solving a quadratic equation. First off, how do you know that you have a quadratic equation? Not necessarily just a zero. There's one telltale sign of a quadratic equation. It's second degree, so x is what? Squared. Right? If I see a second degree meaning x is squared, this, I guess you could write on here, it's page 109. You can write it at the top to help remind you, but second degree meaning x is squared. What is a method we can use to solve that quadratic equation? Okay? What's the first method most of us try to jump to? AC method of factoring. Now, what do we have to have in order to use the AC method of factoring? We have to be able to factor, yes, but what does that equation have to equal? So AC method of factoring if equation equals 0. To do what? What's the goal with that? If we're going to use that AC method of factoring, what's our goal with that? To use what? Zero product property. You've got to know what that zero product property is. You have to know why it works and what it means. That is the big picture. Now, do you need to take the time to practice the AC method of factoring? Yes. But practice it. We've done a lot of that practice. There's lots of videos on YouTube where we're working problem after problem after problem. You don't need new problems. You don't need more problems. You need to understand how this concept works. So go watch one of the YouTube videos, write down the equation that we're trying to solve, and work it out on your own, and then check against the work that we talk about. That's how you develop understanding of this. 2. What other methods do we have available to us? Vertex form. So convert from standard, right, to what? To vertex form. And big picture, what's the first thing that you should write down? Because there's a whole lot of stuff you would have to memorize if you want to just memorize it all the way through. Big picture, what do you want to write down if you're converting to vertex form? Vertex form, right? Which is? And that should be your driving force to think through, how am I going to convert to vertex form? Now, I'm going to write those details in a second, but don't forget, when you convert to vertex form, what's the goal? To do what? To use inverses with properties of equality. That's the goal, right? If I'm going to convert to vertex form, is to then use inverses with properties of equality. And we got to pay attention to details. Now, in order to convert to vertex form, what's the first thing that I should identify? Even before H? I'm gonna identify A. You could identify H first, but I tell you what, when A is not 1, a lot of us are messing up because we're missing that detail. I would identify A first. What could I identify second?
H.
H, oh yeah. Because how do we calculate H? Opposite of B divided by 2A. Guys, don't forget, can you write that down to help you remember and identify H correctly? Uh-huh. You know who's most successfully calculating what H is? The ones who write down H equals the opposite of B divided by 2A. It's not a mystery, okay? After I find H, what do I need now? K. And K doesn't have to be terrible. K is just the output when what? Is what? The input, that's it. Once you have your vertex form, you're just going to use your inverses with your properties of equality. What's our final method? Quadratic formula. The reason why I don't jump straight to the quadratic formula is there's a lot more in terms of simplifying, but if ax squared plus bx plus c equals what? 0, it has to equal 0, then x is equal to the opposite of b plus or minus the square root of b squared minus 4ac, all divided by 2a. You substitute in, and you simplify that expression. Guys, that's the entire unit. Here, cool. You engaging? Staring off to the side and not writing this down. That can't be engaging. You wrote all this down.
Oh, I'm not. I just wrote down like what's look up on YouTube. I'm gonna do it.
Okay. Okay. So, that's it. Those 3 things. I know it seems like a lot because there's a lot more that we work out when we write with it, but that was it. Don't make it more complicated than that. That is something that all of you can master. Put in the time this weekend to study some. Shoot me an email if you have questions. I will give you the solutions to these 3 quickly. I would have to memorize them. Nope, they're around the room. So for A, x equals the -4 plus or minus the square root of 2i. Make sure your I is outside of that square root. Okay. I don't remember this one off the top of my head. I don't see the look for it. I think it was it square root of -20 here? That's right. So that came out to be 2 square root of 5i. And then the most simplified version would be this. And then these solutions were actually rational with, 2 and -2/3. So you have practice problems that you can work, try to get those solutions. Now, I will point this out. The fact that I got rational roots here means that I can use what method to solve this equation? It's the first one we learned. Factoring. Rational roots means I could have factored it. So keep that in mind. Yes, ma'am.
What? Right now in B.
Yeah.
It's not a 1 in front of the. Cause then you divide everything by 2.
Yeah.
What happened?
Yeah. So you can, but if I do 1 times 7, what is that? I'm making it up. But if I do 1 times 7, I get 7. So if I do 1 times 20, what do I get? So if I do 1 times the square root of 5, what do I get? So that's the same thing. So I didn't multiply, I just didn't write it. Does that make sense?
But can you write it?
Yeah.
Okay.
Yeah, it's totally valid mathematically. Good question. All right, went a little bit longer on that than I meant to, but we're actually going to go to the next page in the book, and we're going to talk through a couple of details that are really going to inform the next thing that we do.
Is this going to be on the test?
Yes and no. What I mean by that is I'm not directly testing you on it, but it's going to be helpful for you on the test. Okay? So this key term here will not be on this test, but it is on your next test for sure. And these concepts are things you already know, we just haven't named them yet. So remember guys, math is just the study of what? Patterns and relationships. This is a pattern and a relationship you've already actually seen, we just haven't named it yet. So the fundamental theorem of algebra states that any polynomial equation of degree n must have exactly n complex roots or solutions. And any root may be a multiple root. So, what type of function is this? Huh? So that's how many terms there are. But what type of function? It's the standard form. But the type of function? Quadratic. And it talks about a degree over there. What's the degree of a quadratic? Second degree. So how many roots does that equation have to have? That's what that says. The fundamental theorem of algebra, that's a fancy way to say whatever the degree is, that's how many roots it has. Whether they're real or they're complex, it has that many roots. So if I were to think about this function, anybody know what the degree of that function would be? Close. I know why you're thinking that. But remember, this is x to the first. Did you add those exponents? To the fourth degree. This was second degree, right? Whatever the highest degree is in standard form, that's the degree. So this is fourth degree. So how many roots would that one have? That's it. That's all that thing is saying. So if it was seventh degree, how many roots would it have? 7. That's it. So here, looking at this, notice when we have the vertex above the x-axis and it's concave up, how many x-intercepts did it have? It had 0 x-intercepts, but how many roots does it still have to have?
2.
So both of them had to be imaginary. Here, when the vertex is above the x-axis and it's concave down, how many x-intercepts does it have? 2. So, how many roots does it have? 2. Are they real or imaginary? They're the 2 x-intercepts, 2 real roots. So notice the link. This isn't new information, it's just formalizing what we've already learned. And what key idea is telling us all of this? What's the term up there? That's bolded? That's all it is. Fundamental theorem of algebra. That's the defining characteristic of algebra. It's fundamental to everything we study. Okay? So if my vertex is below the x-axis and it's concave up, how many x-intercepts?
2.
Okay, number of roots and types. Anybody want to push back on or add on to that? Ask a question about that? Good. Hayden, you good with that? Hayden, where would those 2 real roots be on the graph? Yeah, x-intercepts, good. Like, that's what we want to recognize. Okay. Vertex is below the x-axis and it's concave down. How many x-intercepts?
0.
Types of roots? 2 imaginary. So now the vertex is on the x-axis and it's concave up. How many x-intercepts? But how many roots does it have to be? It has to be 2, so what do we call that? A double root. Still 2 roots. So now we have a vertex on the x-axis and it's concave down. How many x-intercepts? Roots? Double root. Okay. So if we have a quadratic, how many roots, how many zeros do we always have to have?
2.
Always has to have 2. What is telling us that? The degree tells us that based on what key concept? The fundamental theorem of algebra tells us that the degree and the number of roots are the same. That's what it says. That's it. Fundamental theorem of algebra. Okay? And the reason I'm bringing this up is we've been studying quadratics. We studied linear before. We're about to go into higher degree. We're going to go into cubics and quartics and quintics, which are just fancy names for 3rd degree, 4th degree, and 5th degree. Okay. Not have time for those. Did that with you yesterday. So we are skipping a lesson in the book, but we are going to page M1-139. The first lesson is not necessary in the next topic, so we're jumping straight to M1-139. All right. To be fully transparent with you, I like the concepts of the lesson in the book, but I did not feel like the book helped all my students last semester, so I created a TI Inspire file that I just sent to your calculators to help us learn these concepts better. What we are looking at right now is we're looking at translating and dilating functions by non-constant values. So let's talk about this. So pause on the calculators. I want you to understand a key idea. What do we mean by a translation in mathematics? David, are you serious? We're an hour into class and I just now noticed you got headphones in? David. Thank you, sir. What's a translation? What does that mean? Okay. So that's translating language, right? And you can translate from one mathematical representation to another. But let's say I have a square. What would it mean to translate that square? How? Move it? In what way?
Copy it.
And the way we copy it is shift it right. Or we could even shift it down. We can translate it left or translate it up, right? Translations are shifts, moving around the coordinate plane. When we look at the most basic quadratic equation, it's right there. There's my vertex. But remember how sometimes our vertex was over here? What caused the vertex to move? Which part of that vertex equation? H and K. What operations are happening with H and K? Guys, operations. Addition, subtraction, multiplication, division, exponents. So we're multiplying here to translate. That's what's called changing the H and the K. Huh? We're adding or subtracting. Guys, like, come on. So if you hear the word translate in mathematics, you need to be aware that we're talking about addition or subtraction. That's what we mean. So to translate a function around, right, to move that vertex and the rest of the points, we're going to look at the addition and subtraction. The dilation, right? We're talking about stretching or shrinking. So if I take that square and I make it bigger, that's called a dilation. What mathematical operation could make something bigger or smaller? Just make a prediction. Okay, or multiplication, right? Multiplication and division will create dilations, make things bigger or make them smaller. Now, all of these concepts are tied into constant values. What we're looking at is a non-constant value. What do we mean by non-constant? It doesn't stay the same. What's a mathematical thing that doesn't stay the same? Talk about them in your science classes as well. Say it louder. Independent and dependent variables, right? We're focusing on the idea of variables. So when we've done translations or dilations in the past, yes, we use symbols to represent things that could be different, but they were always constants, right? Thanks. Right? This would translate the vertex to the right 2. This would translate the vertex up 5. That's why you get the vertex there. It actually translates all those points. This 3 right here is a dilation. It's going to stretch my parabola up. But what happens when we do things that are non-constant? What's that going to create? Higher degree functions. We're going to do stuff with non-constants to create higher degree functions, and I have created a T-Inspire file to help us do that. We're going to look at how to figure out what the graph would look like just based on the factors there. So, here's what we have in the book. They have this is on the getting started, it's on the next page. We're considering a function, f of x equals 3, it's a constant function. And it's going through there. Notice right here how they're adding something to that 3, to that constant function. Addition creates what type of transformation? Adding and subtracting creates a... Not dilation, adding and subtracting. Translation, what created dilations? Multiplication, right? Addition and subtraction create that translation. But notice we're translating by a variable. So what does that do to this function? This is what I created the T-Inspire file for. So if you go to the very first page of the T-Inspire file, is this what it looks like currently? Yes. Okay. So, say again.
I don't think I got it.
Are you logged in? So go to my documents. Go to this class. So spring first block. Let me see. There it is. Okay. So what I want us to notice is, first off, this constant function right here, this blue line, that's like what's in the book. F1 of x is equal to what? A. Here's a slider for A right here. Just play around with A. Tell me what it does to the function. Okay? Documents, or browse. That's it. So play around with A. Why didn't I do it? Okay, guys, go to Spring 2022, Lesson 2, as dynamic graphing. So when you go to your documents, go to Spring 2022, and it's called Lesson 2.
Move the K.
Say enter. Say again.
Move the K.
When you say K, what do you mean?
The Y value.
The Y value? Now, you say the Y value, the vertex. If you say a vertex, what type of function do we have to have?
Quadratic.
Do we have a quadratic up there?
No.
No. So let's think about some other predictions. What's A doing to this function? What else do we see is happening? Actually, do this for me really quickly. Click on the f2 of x, that red equation, and click on the box so that the red, so you see how it's check marked? Click on that so that goes away. So we can just focus here. Now move A around. What is changing A doing? I'll send it back out. I don't know why I didn't get it. Did anybody else not get it? Desiree didn't get it at all. So what is A doing to that function that we see there? Don't save it. Just hit enter and don't save. Guys, y'all are making this too hard. What? It's translating that function up and down. That's it. I want you to notice right now, what is my A value?
4.
4, thank you. Where do we see that A value in this equation? It's the y value, it's the y-intercept? Notice it's also the y value right here, isn't it? Because literally, what does f of x stand for? That is y. So we're saying y is equal to, what is my A?
4.
So what is every y value right now?
4.
That's it. So now let's change A again. Now A is a -2. What do you see about every point here? What's -2 though? Because the x is -2 here, but every y value is -2. That's what I want us to see. Okay? So now let's put that red function in there. What it says in the book is to consider the point of the original function at x equals -1. This point has the coordinates -1, 3. We don't care about that much. But it says translate by x. So what operation do we need to do for a translation? Addition and subtraction, thank you. So do this for me. Hit the menu button and go to graph entry / edit and go to function and go up to f2 of x. So you just hit the up arrow until you see this f2 of x. Click on that checkbox. I got it. Click on that checkbox so that your red line is showing again. Yes, sir. Does anybody need Ms. Bauer to come by and help them make sure that that line is there? Do we all see it? So, yes, Jalen? We only have 13 minutes left. Can't hold it. So, when we added x to it, what happened to our function? What do we notice? Guys, I need you to engage. I need you to actually think. I don't care if you're right or wrong. Just try something.
What'd you say?
What did adding x do to f1 of x? Okay, not just that. You are correct, though. I hadn't even thought about that. Okay, that's interesting. So they both have a y-intercept of -2. Does everyone have a y-intercept of -2, though?
No.
No? What's your a value? -1. Okay, but now they do both intersect at 0, -1. Is that a pattern that holds up, I wonder? What's another a value I can try? 1? Still doing that. Try some other values. Do we see that these two lines have the same y-intercept all the time? Yes? Miracle, you trying it? Try on? Guys, this is where learning starts. If you don't do the beginning, you're going to get lost later. Yes, Hayden? Where? Do you not have the...
Oh, I know why.
There you go. Why? Okay, so that's a huge part of it. Yeah, F1, the y value does equal what? What does f1 of x equal? Well, it equals a, 1 right now, right? And so you say that you know why, it's because f1 of x equals a, but we're also looking at f2 of x, right? What could I substitute here in the place of f1 of x? Say again? Does f1 of x equal a? So I can substitute that in. f2 of x is equal to a plus x. So literally I'm taking the a value and adding what to it? X. Hey, right here, what is the x there? The x value. At the y-intercept, the x value is 0. Hey, what do I get if I do 1 plus 0? I get 1. Right? Let's see if that pattern holds up later. Let's look at this point right here. What's this point? 2, 1. What's 1 plus the x value of 2? Is that this point right here? 1, 3. So we have this point over here, -2, 1. I take my a, 1, and I add it to, or I add -2 to it. What do I get? No, that's a -2. Don't forget, you can hit the scratch pad, little calculator button in between escape and tab to get to a scratch pad. What is 1 plus -2? -1. Is that what this point is right here? 1, -1? So literally what's happening to the blue line right here, we're adding x to it. And it changed that function. Okay? So when we add and subtract, multiply and divide by variables, it's going to change the type of function. That's what we want to see. And all we're doing is we're taking the y value, f1 of x, that stands for what? Y. f1 of x is y. And then we are adding x. That's it. And we can see that by manipulating this function around. So are there any key things we need to write down here? So notice that answer is number 4. Where have all y'all been? Huh? Oh, y'all are doing that today, got it. Okay, what point does not change its location from the original function to the new function? Which point did it change? Come on, is the first thing y'all noticed? So when we looked at the blue function, the blue line, what point did not change from the blue line to the red line? Look at, trying to think of how to help us see this more clearly. When you say -2, like, here was an x of -2, right? Did that point stay right there on the red?
Oh no, it was the A, the Y.
The Y.
Axis, or intercept.
There we go, y-intercept. See how those are the same points? Yes, Mr. King, they're literally the same point, guys. Why was that? Because all we did was add x, and at the y-intercept, what was x? 0, thank you. Woo. Okay? So what point does not change its location? The y-intercept. Because we added x, which was 0. That idea of something staying the same is critically important. Hey, Tevin, you were supposed to put that up when you walked into class. Thank you, sir. Okay. Notice one other detail we need to add here before we move to activity 2.1 is this. Originally, that blue function, yes, it was a line, but it was also called a constant function. right? We had a constant function f of x equals, and we used a, right? But then we went from a constant function, I will point out, do you know what degree that function is? Might think 1, right? But do we have an x there at all? So remember, if it was x to the second, that was what degree? Second degree. If we have x to the first, that would be what? If it's second degree, because it's 2, so it'd be first degree. Degree 1 or first degree is how we would say that. So first degree there. So if we do not have an x whatsoever, we would call that a 0th degree, or degree 0. That's not how you spell degree. So that's degree 0. But adding x, so let's call it g of x, that was just taking f of x and adding what to it? What do we add to f of x to get our second red line? We had a, and we added x. Or that means we had a plus x. So we had a 0th degree, we added a, what degree would this be? A what? First degree. So now we have what type of function? A first degree. The whole point of what I want us to see is we can create a higher degree by adding, subtracting, maybe multiplying, dividing by a polynomial, is what it's called. By an x to a power. We are creating new functions by simply adding or subtracting, or in this case, we'll be multiplying the majority of these. Okay. Questions before we look at one last thing to wrap up today. So the next part of the book is where the real reason why I created this, and I just want us to look at something. We don't have a ton of time. Do notice right here, okay, it's now talking about dilating a function. Dilating. By multiplying the function by a constant. Now we're going to dilate by a variable. So if I have f of x equal to x plus 3, what degree is that? First degree. What type of shape would we see on a graph? Straight line. You can just say linear, right? A linear function. And what are we doing to f of x according to these instructions right here? Dilating, so we're going to what? Multiply by, look at the instructions here in the second paragraph, by x. What degree is that? First degree. So I have a first degree times a first degree, a line times a line. What type of function do you think that might create? Second degree maybe? So you're thinking it might create a what? If it's second degree. A quadratic, a parabola then? So this we're going to wrap up. So we're going to do more of this on Monday, but I want you to see right here. You see this blue line? That this is something that's already on your calculators, and I'll put it back out on Monday. But you see this blue line right here? See this red line right here? So that's, I called this, I think blue was f1 of x, red was f2 of x, and what are we doing? We are multiplying, so that's a dilation. If I take a line and I dilate it by a line, what do I create? A parabola. That's a key thing that I need you to understand. If I take a first degree times a first degree, I get a second degree. We're going to look at how to graph those things and make sense out of those on Monday. But what's the first thing we're doing on Monday? Taking a test. Please take advantage of the weekend to study. That's the whole reason I'm giving you an extra weekend. You got 45 minutes on Monday to do a few short answer. You got some questions like the understanding check. Naisha and Sanaya, Tevin, get your understanding checks before you leave. I did not get to score them, but I made scans of them. I'll score them later, but we did go over them yesterday, right? All right.
Oh, so thanks for making me cry yesterday.
Please note the assignments.
Thanks for making me cry. No, I was saying like real thanks, because I needed it. Now I
Tevin
don't
and
care anymore.
Naisha. Hey, if anybody, David, you were here this whole time. Why did I not give a secret? If anybody sees Tyson